Hello geometry students. In this video we're going to take a look at our 3.5 and 3.6 notes. So have your notes ready and let's go ahead and get started. Before we get started, I just want to review what we've talked about earlier in this unit. We've talked about what happens when parallel lines are cut by a transversal. So remember, when we have a pair of lines that are parallel, and remember how we indicate parallel lines is by putting arrows on the line. If we have a couple of parallel lines cut by a transversal, that transversal and those parallel lines create a whole bunch of angle pairs. And remember, we learned that if the lines are parallel, we've learned that first of all, corresponding angles will be congruent. Okay, we've learned that alternate interior angles will be congruent. We've learned that alternate exterior angles are congruent. And then finally, remember those same side interior angles, or sometimes they're called consecutive interior angles. Same side interior angles aren't congruent, but they are supplementary. All right, so just a review of supplementary. There we go. I can't talk and write at the same time. So just a review of what we already talked about in this unit. Now, what we're going to talk about today will be the converses of, remember this this first was a postulate, okay, and then these three were theorems that we've proved. So what we're going to talk about today are the converses of all of those. Okay, so let's start by first taking a look at this scenario. So we have two athletes in a rowboat, okay? The two athletes want their oars to be parallel. So what adjustments do you think we could make to guarantee that their oars are parallel? So you'll notice that athlete A, his oar forms a 58-degree angle with the bottom of the boat. And the second athlete, athlete B, his oar makes a 60-degree angle with the bottom of the boat. So what adjustments do you think could be made? Well, let's start by talking about athlete A. Athlete A could make a minor adjustment here. What if athlete A just tilted his oar a little bit, so instead of a 58-degree angle, it were a 68-degree, sorry, not 68, but a 60-degree angle? Well, what that would mean then is that these oars would have to be parallel. So either we could say that athlete A could change his oar to a 60-degree angle, okay? Or we could take a look at athlete B. He could change his slightly and change his oar to a 58-degree angle. If either one of those athletes makes that adjustment, then what that would guarantee is that the two oars would be parallel. So that is an illustration of our first postulate called the converse of the corresponding angles postulate. Here's what it says. If two lines are cut by a transversal so that corresponding angles are congruent, okay, then that's going to guarantee that those lines are parallel. And you can see that that is the converse of the corresponding angles postulate that we saw a couple of days ago. Now, when we go to write justifications, either in your homework or in perhaps as reasons in a proof, we don't want to have to write this big long postulate, but I need to know what you're thinking. So I'm going to ask you to not just write the name of the postulate, but actually write the postulate in shorthand. So here's how we'll write that postulate. We will just say, whenever corresponding angles are congruent, okay, that will imply that we have parallel lines. Now again, we are assuming the existence of a transversal. If we didn't have a transversal, we wouldn't even have corresponding angles. So draw a box around that. That will be the shorthand way that we write the corresponding angles postulate. Okay, so now let's look at these next three theorems. The alternate interior angles converse theorem says, if two lines are cut by a transversal so that a pair of alternate interior angles are congruent, then those lines are going to be parallel as well. Okay, so how will we write that in shorthand? We'll just say alternate interior angles congruent implies parallel lines. All right, draw a box around that. That will be the way that we write that theorem in shorthand. The alternate exterior angles theorem converse says, if two lines are cut by a transversal so that a pair of alternate exterior angles are, I bet you can guess what's going to go in this blank, are congruent, then again we can conclude that those lines are parallel. So put congruent in this blank and parallel in this blank. And then how are we going to write that in shorthand? We're going to say alternate exterior angles congruent implies parallel lines. And draw a box around that. And then last but not least, we have our consecutive or same side interior angles converse theorem. Here's what it says. If two lines are cut by a transversal, so that again, well, not again, but so that a pair of consecutive or same side interior angles, this time we're not going to say are congruent. This time we need to say that they are supplementary. Should have made this blank a little bit bigger. Sorry about that. You can abbreviate if you want. But if the same side interior angles are supplementary, then we conclude that the lines are parallel. So how will we write that? As in shorthand, we will just say SSINT, that stands for same side interior angles. Let's go ahead and abbreviate supplementary. If that's true, then we can conclude that our lines are parallel. We have parallel lines. So draw a box around that, and that is how we'll write that theorem. Now in your 3.2 proofs worksheet, you might recall proving a theorem called the perpendicular transversal theorem, which said if two parallel lines are cut by a transversal and that transversal is perpendicular to one of those two parallel lines, it has to be perpendicular to the other line as well. So again, that theorem, the hypothesis of that theorem was that we had parallel lines. The conclusion was that if the transversal was perpendicular to one of those parallel lines, it's perpendicular to the other one as well. Well, this theorem, the perpendicular transversal converse theorem, is just the converse of that. It says in a plane, if two lines are perpendicular, perpendicular, see if I can squeeze that in there. If two lines are perpendicular to the same line, then those lines have to be parallel to each other. Okay, so how will we write that in shorthand? Let's just write. To write this in shorthand, we'll say that, let's see, two lines that are perpendicular to the same line, we can conclude are parallel lines. All right, so that's how we'll write that converse in shorthand. All right, so let's go ahead and take a look at some examples where we're going to apply these theorems in the one postulate. The directions say, given the following information, determine which lines, if any, are parallel. And that's important. It says, if any, are parallel. So sometimes you might not have parallel lines, so be aware of that. State the postulate or theorem in written form, so that means you're going to write one of these shorthand versions that justifies your answer. Okay, now, if you're going to mark your diagram, you might want to use a pencil. It's going to be easier for me to erase each time, so I'm going to go ahead and mark it, starting with example A, where we are told that angle 1 is congruent to angle 6. So I'm going to mark angle 1 congruent to angle 6. If you do that, I would recommend, again, that you use a pencil so you can erase it. Okay, so if 1 and 6 are congruent, first of all, do you all see the transversal that created those angles? It would be line P. And so if 1 and 6 are congruent, well, what kind of angles are those? Well, it looks to me like they're on alternating sides of the transversal, and they're on the exterior of lines L and lines N. So what we have is a couple of lines cut by a transversal such that alternate exterior angles are congruent, so we can make the conclusion that these two lines, L and N, are parallel. So we will say that L is parallel to N, okay, and then we need to write a justification. It'll look like this: alternate exterior angles congruent implies we have parallel lines. All right, now let's take a look at letter B. So letter B says this time we have angle 2 congruent to angle 3. So I'm going to mark those. Here's angle 2 and here's angle 3. So it looks like 2 and 3 are on alternating sides of this transversal P, and transversal P creates these angles with lines L and M. Now, what kind of a pair of angles are they? They're on alternating sides of the transversal, and they're on the interior of lines L and M. So, looks like we have two lines cut by a transversal such that alternate interior angles are congruent, so we can conclude that those two lines, line L and line M, are parallel. So we will say that L is parallel to M, and the reason we'll give is that when this time alternate interior angles are congruent, we can conclude that we have parallel lines. Okay, now let's take a look at letter C. So letter C says this time we have angle 1 congruent to angle 5. So let's mark those. Here's angle 1 and here's angle 5. So this time it looks like we have transversal P creating a pair of angles with lines L and N. Now, if you look at 1 and 5, it looks like they are occupying corresponding positions. They're both on the left side of the transversal. They're both above the lines that are being transversed. So 1 and 5 would be a pair of corresponding angles. So because of that, we know that the lines that form these angles with line P, line L and line N, would have to be parallel to each other. So we're going to say that those two lines, line L and N, are parallel. And then we need to give a reason. The justification would be when corresponding angles are congruent, we can conclude that we have a pair of parallel lines. All right, and then last but not least, let's take a look at letter D, where this time we are told that angles 4 and 5 are supplementary. So I'm going to put one arc on 4 and 2 arcs on 5. Notice this time we weren't told that the angles were congruent. We were told that they were supplementary. Well, so what's going on here? I have line P intersecting lines M and N such that I have a pair of same side interior angles that are supplementary. So because of our theorem, our same side interior angles converse theorem, we can conclude that lines M and N are parallel. So we will say that M is parallel to N, and our reason will be that when same side interior angles are supplementary, we can conclude that we have parallel lines. Okay, for example 2, what I'd like for you to do is in just a minute, I want you to actually stop the video and work these examples on your own. And then when you turn the video back on, you can check your answers with my answers. So once again, the directions say, given the following information, determine which lines, if any, are parallel, and then state a postulate or theorem in written form that justifies your answer. So you might be given some information that does not create parallel lines. If that's the case, then you would just say no parallel lines. So what I want you to do is stop the video, try these, these six examples on your own, and then turn the video back on and check your answers with my answers. Okay, so check your answers and see how you did. As you're looking them over, if you see one that you disagree with me, you might want to stop the video and think about it for a while. You might want to discuss it with one of your neighbors. And if you still can't figure out why you made your mistake, just put a mark so that you can ask me about it next time I'm back at school. Okay, so hopefully you had success on example number 2. So let's take a look at one more example, example 3. Okay, which says the following. It says, find the measure of angle MRQ so that A is parallel to B. Okay, so MRQ, let me just mark that angle. MRQ is this angle. Nope, not that one. Sorry, let me erase that. MRQ starts. MRQ is this angle right here. Okay, so what we need to do is, first of all, find a value of x, and then plug that x in to see what the measure of angle MRQ has to be so that I have parallel lines. Well, these two lines, A and B, are going to be parallel if this angle and if these two angles that I'm marking in red are congruent. Those angles that I have marked in red are alternate interior angles. They're on alternating sides of the transversal and on the interior of the two lines being transversed. So if those two alternate interior angles are congruent, then I have parallel lines. So let's go ahead and solve for x. Let's take 5x plus 7 and set that equal to 7x minus 21. Now I have an x term on both sides. Why don't we eliminate one x from one side? And we'd have 7 equals 2x minus 21. Add 21 to both sides. And we get 28 is equal to 2x. And then we divide both sides by 2, we get x equals 14. Okay, so now as long as x is 14, x is equal to 14, then these two angles would be congruent, which makes lines A and B parallel. Now notice that it says find the measure of angle Q. We haven't done that yet. All we have done is found x. So what we need to do is go back to this expression for the measure of angle MRQ, and where you see this x, let's replace x with 14. So that would tell us that the measure of angle MRQ is equal to 5 times 14 plus 7, which is, let's see, 5 times 14 is 70, and then 70 plus 7 is 77. So the measure of angle MRQ would have to be 77 degrees in order for lines A and B to be parallel. So let's move on to our 3.6 notes. And to start with, we're going to do a quick write. So in just a second, I'm going to have you stop the video and respond to this prompt here. But first, let's take a look at the scenario. We have a football player who needs to get out of bounds as quickly as possible. Of course, when you run the ball out of bounds, that's going to stop the clock. So it must be near the end of the game, and his team needs to get the clock stopped. So he's looking at all his options. There's players, in the way. And so he has several paths that he can take to get out of bounds. So he wants to get out of bounds as quickly as possible and stop the clock as quickly as possible. So I want you to respond to this prompt. First of all, which path, A, B, C, D, or E, do you think the player should take? Okay, so choose one of the paths. Tell me why you think he should take that path. And then think about this question. What relationship does the path that you chose have with the sideline? So you're going to pick one of these paths and then think about what its relationship is with the sideline. So if you would stop the video right now and take a few minutes to respond to this, and then when we come back together, I'm going to ask you about what you wrote. Okay, so next time together, I'm going to ask for some of you to share your thoughts. But I'm hoping that most of you realize that the path the football player wants to take is path D. Path D appears to be the shortest distance from where the player is to the sideline. Now, what relationship does D have with the sideline? Well, hopefully you realize that path D would be perpendicular to the sideline. So that scenario sets up our definition of the distance from a point to a line. The distance from a point to a line would be the measure of the perpendicular segment from a point to a line. So for example, let's say we just had a kite flying in the sky. Well, it's supposed to be a kite. Hope it looks like a kite. There's the thing. Here's the ground, okay? So what is the distance, the shortest distance from the kite to the ground? Well, that would be the measure of this segment, the segment that's perpendicular to the ground. So the definition of the distance from a point to a line will always be the measure of the segment that's perpendicular to that line. Okay, now this next example, we're actually going to do this next time that we're together, because I'm going to teach you how to do some new constructions, all right? And then we'll use our compasses to actually construct the shortest possible path from the foot of this flagpole to the edge of this landscaping, okay? So what we'll do is we'll use our compasses to construct a segment that would be perpendicular to the edge of the landscaping, because the shortest distance from the foot of the flagpole to the edge of the landscaping would be the measure of the segment that's perpendicular to that edge of the landscaping. So just put this example on hold for now, and we'll do it next time we're together. And now let's look at, well, let me make this a little bit bigger so you can see it, sorry. Now let's look at an alternate definition of parallel lines. Remember, the definition of parallel lines that we've been working with says two lines are parallel if and only if they are coplanar and they never intersect. Well, here's another way of looking at it. Lines are parallel if and only if they are everywhere equidistant. See if I can squeeze it in there. Everywhere equidistant. So a good example of that would be this ladder. The sides of the ladder are congruent because each one of these rungs has the same measure. We're told that AB is equal to CD is equal to EF is equal to GH. Let's go ahead and rewrite that in terms of congruency. Let's say that segment AB is congruent to segment CD, which is congruent to segment EF, which is congruent to segment GH, okay? So I'm going to use tick marks to mark all of those rungs congruent. So I hope you can see from that then that these two lines, the sides of the ladder, are everywhere equidistant, okay? So if they are everywhere equidistant, that tells us that the sides of the ladder are parallel. All right, and then let's finish up with this theorem. The theorem about two lines that are equidistant from a third line. Here's what the theorem says. It says, in a plane, if two lines are equidistant from a third line, then the two lines have to be parallel to each other. Let's draw a picture and rewrite this theorem in terms of that picture. So what we're going to draw is we're going to draw a picture of two lines that are equidistant from a third line. So go ahead and draw a line. Let's call that line L, okay? And then draw a line M. Actually, let's call this line, let's go ahead and call it M. And then go ahead and draw a line N. And I want you to draw a line N so that lines L and N are everywhere equidistant from line M in the middle, okay? So how would we write this theorem in terms of this diagram then? We would say if we have two lines that are equidistant from a third line. So let's say that L and N are equidistant from line M, okay? Then what can we conclude about L and N? Let's see, L and N are equidistant from line M, so our conclusion then is going to be that line L is parallel to line N. Okay, so now what I need you to do is go ahead and take your 3.5, 3.6 worksheet and give that a try. Do as many as you can. If you have questions, just make a mark by the ones you have questions about, and we'll address them when we're back together next time. Thanks for your attention, and good luck on your homework.